I did my very best. So let's start this talk, and let me introduce Harald Welte. He is talking about some examples of smartphone hardware and his efforts to dissect them and analyze what's done. So please have a welcome to him. Yeah.
Well, hello everyone. Thanks for the introduction. I'm very happy to speak here at, I think, what must be the 11th CCC Congress that I'm attending. So if you didn't manage to grab a seat and you have to stand, I can offer you as sort of, well, I have to stand by myself as well, so. Anyway, yeah. As the introduction said, this is going to be a talk about smartphone hardware. As many of you know, I have been involved with OpenMoko for some time. But this is not an OpenMoko talk, just to be precise. I mean, OpenMoko is one example. There's going to be more examples, and I will talk fairly generically about how smartphone works. So this is just my usual slides about what I do and what I have been doing. With regard to mobile phones, I first really got in touch with doing anything mobile phone related in 2003 when, while doing my usual GPL enforcement work, I was having problems with a certain Motorola phone that had Linux, so I started to get interested in the phone. Before that, phones, I don't know, I rarely use the phone anyway. So, well, then I started OpenEasyX because we wanted to have a proper open source distribution for the open source Linux system on those devices, and there were more and more devices coming out in this, what Motorola calls EasyX architecture. In 2006, I had the opportunity to buy a GSM-based transceiver station, which is something that I'm going to talk about tomorrow. I've been working for OpenMoko as a lead system architect that includes both the hardware and the system-level software for some time. And now, right now, I'm working on a project which I call GNUfish, which is about porting Linux to a certain series of devices manufactured by E10, designed and manufactured by a company called E10. Well, and right now, this is why I've just come up a minute before my talk. I'm working on running our own GSM test network in the Hack Center downstairs. See the talk tomorrow. So, smartphones, what are smartphones? Unfortunately, there's not a very clear terminology. You know, oh, a smartphone is a phone that has email, but then how many phones don't have email today? It's not really a clear definition. So many people in the technical community, they say, well, a feature phone is something that has a single CPU, a single operating system, and where the entire GSM stack, plus the user interface, plus all the applications run on a single CPU. Those systems are typically extremely closed because certain commercial entities in the mobile phone market tend to be very closed. And thus, development of applications or additional applications for these kind of phones is very hard because they don't really want to run your code on the same CPU as the GSM stack is running. What I call smartphone, also for the remainder of this talk, are phones that contain two main processors, which is one CPU core that actually implements the network protocol, like the GSM, UMTS, HSDPA, HSUPA, and so on network, and another CPU core which actually runs the user interface and applications and so on. So what you can say basically is that a smartphone is something like a traditional old-fashioned GSM feature phone, which some people then also call GSM modem, and a PDA in one device, something like that. That's basically what you get. It's important for me to outline this, also is the idea why I came up with presenting this talk here at the CCC, is that even in the technical communities that I tend to meet people in, a lot of people were in the misconception of, you know, that somehow the network stack runs on the application processor, or that there's no real distinction. So it's very important to know that in smartphones there is this two different systems basically in one box, but they have a very thin communication interface and they're extremely independent of each other otherwise. So, what kind of components do we have on the application processor side? That's going to be nice nerd porn in a couple of minutes with PCB photographs and so on. So, There is an application processor, it's what people typically call it, AP, which in turn mostly is an SoC, a system on a chip. The main manufacturers here are Samsung, Marvell, TI, and Freescale. TI is TI OMAP, people might have heard about that. Marvell is called PXA something, PXA 250, 270, 300 something. PXA was originally the X-Scale design from Intel, which Intel sold to Marvell maybe some 2 or 3 years ago. Samsung has what they call the S3C 24XX and the S3C 64XX, and then they have certain undocumented components which they use in iPhones. You have some amount of flash. Typically, it used to be, or still is to some extent, single-level cell NAND flash. Multi-level cell NAND flash is coming up more and more. It's typically connected to the NAND flash controller inside the system on a chip, which means that this is native raw NAND flash. It's not like a solid-state disk that looks like a hard disk and offers a block device abstraction to you, but it's raw NAND flash, and your file system has to work, or your block translation layer has to work on top of that, because NAND flash has its inherent characteristics. You can't just use it like traditional block devices. So this is not like a USB drive. Oops. Sorry for that. Then you have RAM. Typically, it's still mobile SD RAM, but mobile DDR is becoming more and more an issue right now. So phones with DDR memory are not, are not unheard of. The mobile in the respective RAM name only indicates that there are certain features regarding power consumption, suspend, and so on. So, for example, there's things called partial array self-refresh, where when the processor suspends into RAM, you can refresh only half or a quarter of the RAM if that's sufficient. So you don't need to refresh RAM that's empty, because refreshing empty RAM just wastes battery. These kind of things. Also, the drive strength, like how many milliamps the actual interface is driven with, that can be dynamically adjusted, and they have all kinds of weird features to save the last couple of microwatts. You have a power management unit, and that one is typically fairly, not complex necessarily, fairly inclusive or fairly big, as in has lots of different functionality and features. Some people call it PMU. I think PMU is an NXP or Philips-inspired terminology. Other people call it PMIC, which I think is more the TI and Wolfson speak. So PMIC is Power Management Integrated Circuit. They usually connect over I2C or SPI with your system on a chip device, and the power management unit typically includes something like, I've seen units up to 27 voltage regulators in a power management unit in a mobile phone. Somewhere between 11 and 14, I would say, is the average number of power regulators that you have. You also, some of them are switching, some of them are linear regulators. And the PMU also often includes an RTC or a touchscreen interface and some minor peripherals like that. You have an audio codec for playback and recording of digital audio. Typically connects over I2C for the control channel, and over a PCM bus, sometimes also AC97, but not very common, for the actual audio data. And most devices obviously have Bluetooth, and Bluetooth is typically connected over UART, in rare cases over SPI. Wi-Fi typically connects over SDIO or SPI. SDIO is basically SD card interface, but not just for storage cards, but for general purpose I/O devices. SPI, I'm not sure how hardware savvy most people in the audience are. SPI is serial peripheral interface. I actually don't know what SPI means. Anyway, it's a 4-line interface where you have master in, slave out, and master out, slave in, and clock and chip select lines. Okay, well, these are the kind of things we see on the application processor side. If we go to the actual baseband side, the baseband processor side, BP, it's AP and BP, you have a digital signal processor, which does the RF baseband signal processing, so things like the modulation, the channel equalization, and so on and so on. But it also does the voice signal processing, so the actual speech encoding, decoding, echo cancellation, and so on and so on. You have a CPU that typically is ARM7 based. Now with the higher end 3G, 3.5G modems, it's ARM9. And that CPU only runs the GSM protocol stack and typically an AT command interpreter for an AT command modem interface. You also have LCM, which is, it's a LCD screen module, and a keypad matrix interface, which is not used in the smartphones because the keyboard, if there is any, or the keypad, as well as the screen are connected to the application processor. But you know, semiconductor manufacturers, when they build these chips, then obviously a single chip should fit multiple applications, so you can go to higher quantities. So they see the same kind of chip in a feature phone where there's no application processor, and then you see this very same chip, you see it in a smartphone where you have an application processor. And then the peripherals like a screen interface and keypad interface, you don't use that, even though it's there. What you also have, obviously, is an RF power amplifier, actually not one, but multiple power amplifiers from multiple frequency bands, not rarely. The power amplifiers basically are in the send stage, so when you want to transmit something on the air, you have a power amplifier for that. There is an antenna switch, which typically is a MEMS SPST switch, which I don't know how many people can parse that. It's a micro electromechanical system, single pole, single thread switch. Then you have the ADC and DAC for the actual analog to digital and opposite conversion for both the analog voice data as well as, more importantly, the baseband side, which is the actual information that you transmit on air or receive from air. Now, how are those two interconnected generically? So this depends a bit on what kind of communication system this device is targeted at. For 2G phones, which is just GSM voice, circuit switch data, and GPRS, the connection between application processor and baseband processor typically is a UART, so it's just a serial line, maybe 115,000 BPS, maybe 230, maybe 460, sometimes around 800 kilobits per second, but that's really high. 921 actually would be the exact rate. So in more demanding communication networks like UMTS and HSDPA, HSUPA, the UART is just not fast enough anymore. We have data rates of up to 7.2 megabits coming in. You don't want to squeeze them over, I don't know, a UART or whatever. So the interface that we happen to see here in many systems is a shared memory interface. Mostly implemented as dual-ported RAM. So you have a particular RAM that has two ports, one to the application processor, one to the baseband processor, and then you communicate over this shared memory region. The other option that we see in some devices, mostly the less tightly integrated devices, is SPI. SPI can easily run at 20, 25 megahertz, sometimes even up to 50 megahertz. If you transfer one bit with every clock cycle, then you can easily get way beyond the 7.2 megabits on that. There's no standard for the protocol on top of SPI, though. There's also no standard for the protocol on the memory interface. Some systems also use USB, but USB is really not the kind of interface you want to use in this device. It wastes way too much memory, and you have problems that it's a very master-slave kind of interface where the master, the USB host, has to enumerate the device before they can talk to each other. So what do you do in case your USB host controller, which is inside the application processor, is currently suspended, but you get an incoming call from the GSM modem? You somehow have to wake up. So you need some kind of GPIO or interrupt handshake to wake up the processor. Then the processor has to enumerate the bus. It can find its USB device and so on. It takes way too much time. So that's a very bad design, actually. Now, let's look a bit at the audio interface. The audio interface is actually an interesting thing to look at. Because most people think, well,